This lesson is going to be about finding zeros of polynomials and multiplicity of those zeros. We are going to be using this stuff then to graph functions afterwards in uh, with using the end behavior test from the other lesson. So after this video, there will be another one where we actually graph a full function out using this lesson with finding zeros and multiplicity, while also using the end behavior leading coefficient test from another video. So with this one, first off, when we say finding zeros, understand when we say zeros, that is the same thing as if I ask you to find x-intercepts. Also, other term that can be used is roots. Okay, all three of those terms should not be, none of those three should freak you out more than one of the, they're all the same concept. Okay, whether I ask you to find zeros or x-intercepts or the roots, I'm saying the same thing for this class. You guys have learned x-intercepts before. The way you find x-intercepts is you plug in 0 for y. Now the reason behind that, just real quick here, I mean you guys know if we're talking about an x and a y axis, x-intercepts would be the points that lie on the x-axis, so like any of those 4 points. Obviously, those points are all different. They're all x-intercepts, they're all zeros, but they're still different points. However, the one thing they all have in common is that they all have a y-coordinate of 0, because that's kind of required, right? If they had any other y-coordinate than 0, they'd be either above or below the x-axis. So that's why the way you find an x-intercept is by plugging in 0 for y. So when you are asked to find the zeros, what I'm really saying is plug in 0 for y, and then solve out. Now the way we're going to do that today is we're going to do that by factoring. You guys have learned multiple ways to solve out zeros by now, more than likely, but we're going to talk about factoring specifically today. So for example, let's say I gave you a function like this. Say I gave you something like that, okay? And I ask you to find the zeros of that function. Well, first off, you need to recognize in your head that when I say find the zeros, I'm saying find the x-intercepts. Once you realize that, then you need to figure out that by finding x-intercepts, I'm asking you to plug in 0 for y, and you also need to know that that would mean f of x in this case, that those are representing the same thing. When I say y, I'm just referring to any output for that function. And in this case, the output for a function is labeled as f of x. So that would mean we've got 0 equals x to the third plus 5x squared plus 6x. And then we're going to want to factor. Now, remember, there isn't one thing that means factoring. Factoring is just another word for dividing, and there's many different types of factoring. In this case, the best thing for us to do first would be GCF, greatest common factor, meaning we want to divide out, we want to pull out what's in common. Because if I look at those three terms, I see that every single one of them has at least one x. So I'm going to pull that x out. That means now I would only have an x squared instead of an x to the third. That means I would only have a 5x instead of a 5x squared. And that means I would just have a 6 instead of a 6x. Now that is factoring right there. That's a type of factoring, so we have started solving for zeros by factoring. We're not done though, because when I look at what's left inside the parentheses, that is something that can be factored even further. Depending on how you guys have been taught or how you've learned it will depend on how you look at this. I always teach it as the x method. You are looking for two numbers that multiply to 6, because 1 times 6 gives you 6, and also add to 5 because that's your b value. Well, two numbers that multiply to 6 and add to 5 would be 2 and 3. So that means my fully factored version of this function would be the x that we pulled out earlier, x plus 2 from our x method, and x plus 3 also from our x method. That would be our function fully factored. I don't see anything that I can factor further in any of those parentheses. Now we want to solve each of those out separately by setting them all equal to 0. Remember, the reason why that works is only because it's equal to 0. Since it's equal to 0 and we know anything times 0 gives us 0 for an answer, if I can get any of these three expressions to give me 0, then I'm still solving out the whole problem. If that doesn't make sense, you may need to go back and watch that video from before or look at those notes from before, but since it's equal to 0, we can set all three of these equal to 0 separately and solve out. It's called the zero product property. So first one, don't overthink that, it is solved out. X equals 0. Second one, we need to just subtract 2 over to get x equals negative 2. Last one, we need to subtract 3 over to get x equals negative 3. It's a bad 3. Now, the other part of this lesson is determining multiplicity. It's a weird word. So multiplicity. The easiest way to define multiplicity is you're basically just answering the question of how many times did I get each answer? How many times did I get, or we'll say each is 0 to be more specific. How many times did I get each 0? That's what you're answering for multiplicity. Meaning, it's not a hard question for this one. I got x equals 0 once, I got x equals negative 2 once, and I got x equals negative 3 once. So all of their multiplicities are 1. Really is as straightforward as that. Now the reason why we care about multiplicity is if you get an even multiplicity on the graph, that 0, or when the graph of that function touches the 0, it's going to go back the way it came. So when you have even, let's write that differently. When you have an even multiplicity, the graph will touch at the 0. Now what I mean by that is, we have a graph right here. Let's say right here is an x-intercept, is a 0. If the graph came from above, when it hits this 0, if it's an even multiplicity, it's going to touch that 0 and then head back the way it came, also heading back up. The other side of that is, let's say you have an odd multiplicity, like we did up here with the multiplicities of 1. An odd multiplicity means that the graph, man, my writing's going bad. The graph is going to cross at that 0. Meaning, if we have a graph like this, and we say this is an x-intercept, if the graph was coming from above, when it hits that 0, it's just going to continue on like it never even knew it was there. Go below the x-axis and keep on going the way it did before. That's the difference. An even multiplicity, when the graph hits the 0, it's going to go back the way it came. If it was from above, it's going to stay above. If it was from below, it's going to stay below. When it's odd, it's going to cross, meaning it'll act like it doesn't even realize that it touched any important point at all. Like it doesn't even recognize it's an x-intercept. Okay? So the reason why we care about that then is that that informs our ability to graph. So examples where you could get an even multiplicity. Let's say you had a function like, let's do this. Well, yeah, we'll do x squared first. Like x squared minus 6x plus 9. Okay, if I asked you to find the zeros of that, well again, zeros means the same thing as x-intercepts. And x-intercepts are found by plugging in 0 for y. So that means we've got 0 equals x squared minus 6x plus 9. If we wanted to factor that, there is no GCF to pull out this time. We can go right into the x method. We'd be looking for two numbers that multiply to 9 and add to negative 6. Well, two numbers that multiply to 9 and add to negative 6 would be negative 3 and negative 3. meaning our factors would be x minus 3 and x minus 3. Or you could also write that as 0 equals x minus 3 squared. Now it really doesn't matter which way you look at this. Either one of those means the same thing. And the ending is still the same. You end up getting x equals 3. Now the reality is, we solved that out twice, right? Whether you see it here because on the first one you actually solve it out twice, or whether you solve it out once with that exponent of 2 right here, you know that exponent of 2 means that you had 2 different x minus 3's. So whether you look at it as an exponent or you actually write it out like you did here, you can tell that you got x equals 3 twice. Now that's not going to show on a graph visually. You're still only going to mark that once, right? If I asked you to graph those, to graph the zeros of that function, you're just going to go out here and put a dot at 3. You're not going to do anything more than that. That's where multiplicity comes in, though, is because the multiplicity allows us to say that the multiplicity is 2, so that means we found the 0, the answer of 3, twice. And so because of that, now I can know that when the graph, if it starts from above, which in this case it would because we have a positive x squared, if the graph's coming from above, it's not going to cross through down here. That's not going to happen. It's going to hit this 0 and go back the way that it came. And that's why the graph looks the way it does. You can go to a graphing calculator and throw in this function of x squared minus 6x plus 9. You'll see that this is what it ends up looking like. Another way that you can get, or just another special case, I guess, recognize that if you have x squared equals 0 or x to the third equals 0, understand x squared really does equal x times x. So that would mean technically you had 2 x's here, which means you find that x equals 0 twice. Likewise, with the x to the third, you've got x times x times x. So technically, you're finding that x equals 0 3 times in this scenario. Just be aware with 0, you're basically just looking at the exponent, and that's the multiplicity of that one. But with any other number, you're looking at how many times did it actually show up. You can pretty much visually see it. Okay, and again, even multiplicity, graph's going to touch, go back the way it came. Odd multiplicity, the graph will cross.